missing work, just a reminder to let me know what you are submitting so that I can update Skyward accordingly, okay? And that I'm not going through every single assignment that we've had. All right. Yesterday, we had 10 practice density problems we should have worked on. If we did not work on those yesterday, or if we had some Canvas issues, because I did get a couple of messages last night saying that Canvas is having some problems, you guys can do those today. They'll be due later on tonight. So by 11:59 p.m. tonight will be when our 10 practice density problems are due. Okay. All right, and then lastly, last announcement, probably the announcement we are all looking forward to, is that this upcoming Thursday, we will have early release. So this upcoming Thursday is early release day. For those of us who are sophomores, usually we would stick around and work on our personal project, but since that is done and over with, everybody gets to go home at that 1:25 time, okay? So we all just get early release day on Thursday. It's some extra time at home, okay? All right. I'm gonna go hit off our lights, give you guys another minute to write down our examples of physical and chemical changes. And then one last reminder, if at any point during the semester we miss a day of class, I do record all our classes. So you can go back, hit that Zoom recording buttons, and then watch the classes that you missed. Right, sometimes we do classwork that I do grade. So be sure to check those things out. Okay. Let's start going over some examples. So does anybody want to share a physical change that they wrote down on their slide? Yeah, pen getting snapped in half. That is a physical change. So you're not changing what the pen is, but you are breaking it, causing a physical change to how it looks. Great example. Any other examples? Anybody else want to share?
I said dissolving frozen food.
Frozen food?
Yes, dissolving it.
Defrosting, right?
Defrosting, yeah.
Yes. Sorry, my volume must be turned down. But yeah, exactly. Defrosting food. What you're doing is changing the state of the frozen food. That's a great physical change. Great example. Okay, what about chemical? Yeah, rusting. That is an example. Any other examples of a chemical change?
I said milk going bad.
Yeah, milk going bad. So when milk spoils, exactly, that is a chemical change. So what's going on in our milk carton as it spoils, as the odor changes, what's happening with the milk is it's no longer going to be drinkable milk. One more time. Burning is a chemical change. So when you burn something, so for example, wood, when you start off with wood, when you burn it, you end up with ash. So that's going through a chemical change because what you started with is totally different at the end. All right, great examples. Anybody have any questions about those? Okay. All right, before we move on to our new material, just a reminder that at this time, phones should be away, headphones should be out. Reminder that I will be paying attention. So not behind a computer screen. If I come up with an envelope, we'll put our distracting items away, okay? Okay. So today, what we're going to do is we're going to talk about the classification of matter. More specifically, we're going to talk about pure substances and mixtures. Right, so we have pure substances. These are things that cannot be broken down into simpler matter using physical methods. So these are things that I cannot break, cannot cut, cannot smash, etc. There are two types of pure substances. So in our text box for this slide, you're going to put down elements, and it's one type of pure substance. We're also going to put down compounds. That's our other type. So pure substances, something that cannot be broken down into simpler matter using physical methods. We have two types, one being elements, one being compounds. Okay. So everybody have that down.
I go to the office.
All right, let's finish writing that down. Okay, does everybody have this written down? All right. So let's talk about these a little bit more specifically. Okay. Paradox being a little slow today. All right, let's first talk about elements. So elements, these are simplest kind of pure substance. We've talked about these before. We have about approximately 110 to be more specific. We have 118 and we're still looking for some. Each are made of a different type of atom, which we talked about with our periodic table. Each element has a name and symbol, and all of us should be a little bit more, should have a little bit more knowledge on a specific element from our element projects. When we talk about our elements, we know that they are not all equally common. So if we look at our periodic table, if I were to talk to you guys about thorium, that's not as commonly known as oxygen. So that's what this slide is telling us, that not all elements are as equally common. So they're not easily as found in our everyday world. When we talk about elements, we talk about how most of them exist as a single atom, for example, iron and copper. But we do have some elements, mostly are gases, that exist as diatomic molecules. So for this slide, for our text box, we're going to define what this term here is. Diatomic. So diatomic, that just pretty much means group of two atoms. That's what we're going to be putting in our text box here. So di, that refers to two. That's what that prefix is. And then atomic just pretty much is telling us we have two atoms. So this is a group of two atoms. So when we talk about our gases, when we've talked about oxygen and hydrogen and fluorine and etc. in the past, those gases, we weren't just referring to one single atom. We were referring to two atoms. So those gases are made up of two atoms of the same type of element. So oxygen, we know as O2, O with a subscript 2. Okay, does everybody have that down? All right. When we talk about our diatomic atoms, we also need to talk about allotropes. Allotropes are different structural forms of the same element. So kind of going off what we just talked about in the previous slide, let's stick with oxygen. Oxygen is known to have 3 allotropes. So when we start off with our first one, and what I would like you guys to do on this slide is to draw what our 3 allotropes are. So starting off with number 1, we'll just have oxygen. So just O. So that is just 1 atom of oxygen. So you can say you have mono. This prefix means 1. You can say atomic, and then oxygen. So here I have 1 atom of oxygen, and that's my first allotrope. My second allotrope would be O2. So my O, my element symbol with a subscript 2, or I have 2 oxygen atoms that are bound together. So here I just draw my 2 atoms, and they're together. And they're fused together, however you would like to depict that. You can say this is diatomic oxygen, or you can just write how we know it, which is oxygen gas. Okay. Then number 3. All we do is just stick on another oxygen atom. So we have O3 here, where we have 3 oxygen atoms that are fused or bonded together. So again, you could say this is triatomic, tri being 3, like a tricycle. Or more commonly, O3 is what we know as ozone. O-Z-O-N-E. Ozone. When we hear the word ozone, we typically hear that when we talk about global warming, or when someone, if anybody has taken Earth and Space Science, that is part of our atmosphere layer. You have the ozone layer. That entire layer is made up mostly of O3, ozone. So for oxygen, we have our 3 types of allotropes. So these are 3 different structural forms of the same element, where we have 1 atom, we then have 2 atoms fused together, and 3 form ozone. Okay. All right. Are you working on other working? Have you been working on other work? Okay. Let's pay attention, okay? All right. So other than these, we have other forms of allotropes. So other than oxygen, here we have examples with carbon. So with oxygen, we talked about different structure by numbering our atoms differently. So going from 1 to 2 to 3 atoms. Here, we can see more 3D how our structure changes. So here are allotropes of carbon. So these are all pure carbon, but they all have different structures. So here in our upper left, this is carbon and it's diamond shape. So this is how that would look if we looked in our molecular level. On the upper right-hand side, we have what we call graphite. So that is how graphite looks. If you were to look at like pencil lead under a microscope, a very intense one, that's what that would look like. Down here, we have what we call fullerene. And then on the bottom right, that is what we call a nanotubule. So pretty much just a very, very, very tiny little tube, all made up of carbon atoms. So this is to show that allotropes are all different structural forms of the same element. I don't anticipate you guys to know the terms that are associated with these images. But if you were to go on in your chemist career and take the class known as organic chemistry, you would study these forms more in depth. Organic chemistry is pretty much the study of carbon and how it interacts with all the other elements on the periodic table. So if you did go on, learned a lot about organic chemistry, you'd be talking a lot about carbon. Okay, so those are our elements. Let's talk about our other pure substance, our compounds. So compounds, these are pure substances that are composed of multiple types of elements. So 2 or more elements that are chemically bonded to one another. So these compounds cannot be broken down by physical methods. However, in our text box, we are going to put they can be broken down chemically. So our compounds, they can't be broken down physically, so I cannot physically grab them and break them, etc. However, I can break them down chemically by breaking the bonds. Our compounds, they have definite compositions, so they have set ratios of the elements they are composed of. We indicate those ratios by subscripts. So an example would be water, we know is H2O. You will never hear water referred to as H4(2) or H2O4 or H3O. It'll always be H2O. That will not change. Water you can break down chemically and separate our oxygen from our 2 hydrogens. But you cannot do that physically. Our properties of our compounds are extremely different from the properties of our elements that make them up. So for example, here, our very first image, we have sodium, which we know as element symbol Na. Way back, when we were talking about the periodic table, and looking at our specific groups and their reactivity, we looked at group 1 elements. When they come in contact with water, they react very vigorously. So most of them burst into flames. If I take that and I add chlorine, which exists as a gas, Cl2. Chlorine gas is used as a war weapon because it is a poisonous gas. If I take sodium and I add chlorine, we get sodium chloride. So NaCl, which we all know is table salt. So we've taken one element which has extremely reactive properties when exposed to water. Another element that exists in the world as a poisonous gas. We put them together and we created table salt. So table salt burst into flames, or known as a poisonous gas. No. So table salt is not harmful to us. And it's quite useful. But it comes from two elements, when added, when separated, have very, very different properties. All right. So those are our pure substances. Let's talk about mixtures. So a mixture is something that can be broken down into simpler materials using physical methods. So mixtures can be made up of three possible types. They can be made three possible ways. By adding an element and an element together, by adding a compound and another compound, or for our third option in our text box, an element and our compound. So if I have an element and I add it to a compound. So mixtures are something that can be broken down into simpler materials using physical methods. We have three possible ways to make mixtures: by adding an element to another element, by having a compound, adding it to another compound, or having an element and adding it to a compound. Okay. We have two types of mixtures. So first type is homogeneous. These parts are distributed evenly throughout. So we can say that the composition is uniform. So meaning that if I looked at that mixture, I can't distinguish what's what. Homogeneous mixtures with liquids are what we call solutions. While homogeneous mixtures of metallic atoms, so let's say if I take any of my metals from my periodic table, I add them together, those form what we call alloys. Examples of homogeneous mixtures, we have salt water, syrup, air, or brass. So first off, let's talk about our salt water. So when you look at salt water after the salt has dissolved, you cannot really distinguish what's the salt and what's the water. But you can physically separate that out by filtering the water and getting the salt to come out. So that is physically separated, but it is a homogeneous mixture because when the salt is added and dissolved, you cannot tell the composition is uniform. Our next main type, we have heterogeneous. So these parts are distributed unevenly throughout. So our composition is not uniform. I can distinguish what and what it's made of. So for example, we have spaghetti and meatballs, water and oil, and trail mix. So when you look at a plate of spaghetti and meatballs, you can distinguish what the meatball is, you can distinguish what the sauce is, and you can distinguish where the noodles are. Water and oil, you can tell that oil is above the water. And then lastly, trail mix. Usually something that you can enjoy. And for people like me who tend to try and pick out the chocolate bits, that is a great way to use the heterogeneous mixture part of it because I can distinguish where those chocolates are, make sure that they're not raisins, not peanuts, etc. Okay. So homogeneous, I can't really tell what's what. Heterogeneous, I can easily distinguish. Okay, and then lastly, mixtures and properties. So before we talked about properties of compounds, how those are totally are different from the properties of the elements that make them up. For our mixtures, our properties of our mixtures are related to the properties of the substances that make them up. So sticking with that water and salt example, the properties of salt stay salt, while the properties of water stay water, even though they are mixed together. So the properties do not change. Unlike with our compounds, when we talked about sodium and chloride coming together to form salt, those properties change entirely. Okay. All right, so it actually changed for you guys. All this morning, this was towards the bottom. Okay, so let's fill out this flow chart so that we have something in our notes so that we can easily distinguish between our pure substances and our mixtures. So let's start at the top. Start with matter, because that's what everything is made up of. We go down and we see we have a question. Can it be physically separated? So I have two sides. We'll have one that says yes. We'll have one that says no. So on our left-hand side, we'll say yes to that question. On our right-hand side, we'll say no. For this question, we'll have two options. So we have to choose between mixtures or pure substances. So can it be physically separated? Out of our options of mixtures and pure substances, if I said yes to this question, that they could be physically separated, would that be referring to my mixtures or my pure substances? One more time. So can it be? And I say yes. Yes, it would be mixtures. So on our left-hand side, where we have our yes, that'll be mixtures. So if I have mixtures on my left-hand side saying yes, that can be physically separated, what would that leave for my right-hand side where I say no, they cannot be physically separated? Pure substances. And then if at any point something is a little hard to see, just please let me know and I can rewrite it somewhere else on the board. Okay, so on our left-hand side, saying yes to it can be physically separated, we have our mixtures. On our right-hand side, we have no, they cannot, so those are our pure substances. Let's stick with our left-hand side. Go down into our mixtures. We then run into the question, is the composition uniform? So that means, can I distinguish what's what in my mixture? So we'll have two arrows going down again. One saying yes. One saying no. So is the composition uniform? If I say yes to this question, that means I cannot distinguish what's what. So for our mixtures, we had two types. We had homogeneous and we had hetero. If I said yes to this question, saying that my composition is uniform, I cannot see what's different. So I can't tell one thing from the next. Would that be homogeneous or heterogeneous?
Homo.
It'd be homo. So saying yes to this question, on the very left-hand side, at this very bottom box, we're going to put homogeneous mixture. And if you would like, you can say that this includes our solutions and our alloys. So if I have homogeneous mixtures over here, if my composition is not uniform, so meaning I can distinguish what's what, kind of like our trail mix, what type of mixture would that leave me? Hetero. So I would have heterogeneous on this side. So sticking to our left-hand side, answering this question, is the composition uniform? To the very left, if we answer yes, we have homogeneous mixture, including our solution and alloys. If the answer is no, so to the right, we would have our heterogeneous mixture, meaning that we can distinguish what's what. All right. Let's move over to our right-hand side. So can it be physically separated? No. Going down to our pure substances. And then looking at our next question. So can it be chemically separated? So we'll have one saying yes, one saying no. Our pure substances, we had two types. We had elements and compounds. So can it be chemically separated? If I said yes to this question, which option out of elements and compounds can be chemically separated? Can be broken down even further. Would that be compounds or elements? So can I take an element off the periodic table and break it down into something even further? So for our no half, we'll put our elements because I cannot break them down any further. I can't separate them chemically. But how about my compounds? So for water, H2O, can I break that H2O apart to get 2 hydrogen atoms and oxygen? So yes, this can be chemically separated. So our chemical compounds, they can be chemically separated. So for our yes arrow, we're going to have compounds. For our no arrow, we're going to have elements. This flow chart will be extremely helpful moving forward, distinguishing between our pure substances and our mixtures. Okay. I will give you guys time to finish copying that down, but for now, I'm going to turn on our lights. Okay. For the remainder of class time today, you guys can use this time to work on our density worksheet from yesterday, our 10 practice problems. For those of us who are here in person, this is a time where we can pull out our phone and our headphones, but be sure we are using our class time wisely. I only did get a handful of those density worksheets turned in. Okay. All right, for those of us who are virtual, you guys can use the time for just copying down what is on the board. And then also use the rest of class time to work on our density problems. Once you have our product done, and if you do not have any questions, you need to ask me. I do not require that you stay on our Zoom call. So you guys are dismissed for the day. So have a great day, and I will see you guys tomorrow.